Dear Heavenly Father, we thank you for the day, thank you for the blessings you've given us, thank you for the students here. Just pray help us in this class, Lord, just guide me in everything we do, in Jesus' name, amen. Alright, good morning to Kim and Wendy. Hope you're doing well. Alright, questions in your homework?
So discontinuity, would the endpoints count? Like there's a discontinuity?
No.
No? Okay. So that's just another. And then 28. And
F of x equals sine of 4x over x. And he's looking for, given a formula for the extension that is continuous at the indicated point, x equals 0. So again, you know, in the initial, sine of 4x over x, right? The limit of that equals what?
4.
4. All right, but we know that if we put, by substitution, put 0 in for x, that's undefined. So I need to know, this is for all when x does not equal 0, I need a function that represents what x is when x equals 0, to fill that spot in. Because right now we have something like this, where it comes up here at 4, and we have a hole. Okay, so we want to fill that hole in, and how are we going to fill that hole in? What expression, what equation can I use to fill that hole in? What is, correct. So that's all we have to do. That would be the function that would fill that hole in. So at x equals 0, f of x equals 4. All the other places, f of x equals sine 4x over x.
Okay. Okay, I guess that's what he's doing.
So we're just looking to fill that hole in.
Can we also do 32?
Exercises 31 to 32 explain why the function is continuous. Okay, so if we look at this, g of x is really 1 over f of x. If we look at it that way. And f of x equals square root of, what did that say, x minus 1. Well, what do we know about f of x?
That is not continuous?
Well, it is continuous if we consider the domain. It is continuous on its domain.
Okay.
So therefore, if f of x is continuous on its domain, then g of x would also be continuous on its domain. So that's all they're asking you to do. All right, where is f of x continuous?
Well, would it be from 1 to infinity?
Correct. So if f of x is continuous from 1 to infinity, then g of x will be continuous from 1 to infinity. And we can put that way. Any other questions?
36 and 40.
Alright, so theorem 7 says if f is continuous at C and G is continuous at f of C, then the composite G circle F is continuous at C. So, first of all, we got 36. F of x equals tangent of x squared over x squared plus 4. Okay, so what is, divide that composition. Let's find f of x and find g of x. What's f of x? If we take this and divide it up into a composition, what's f of x?
I guess we,
Tangent.
x
X squared
over
over
x
x
plus 4, maybe?
Or x, yeah.
X squared over x squared plus 4?
Okay.
And g of x is
X squared plus 4 or x squared.
tangent x.
Oh. Would it work if,
Why would we?
I don't know what I'm doing. I forgot the tangent,
does-
but I had x over x plus 4 and then g of x is x squared.
How does that show it's continuous?
Well, they want you to show it's continuous using theorem 7. So take for instance, alright? So here we want so we're going to say if f of x, pick a number,
1.
2,
Oh.
or 1.
say 2. What's f of 2?
1 half.
1 half. Is g 1 half. Can we take the tangent of 1 half?
Well,
Yeah, we
yeah,
can.
I can.
Alright? They're both the values, right? Is there any place here that is discontinuous?
Right?
X squared over x squared plus 4. Any place there that is discontinuous? Any place where that denominator will be 0?
Oh, no.
No. So f of x is not discontinuous. It is continuous. Alright? What are my values? What is my limit as f of x approaches, or what is my limit of f of x? Let's say to infinities. What's my end behaviors?
I guess going towards infinity would be infinity, because it's getting bigger. So,
Remember, how do I find my horizontal asymptotes? How do I find my limits as I go toward infinity?
B1.
Leading terms, 1. So as I get bigger and bigger and bigger, I'm getting closer and closer to 1, correct? So what is, can I take the tangent of 1? Yes. So therefore, therefore the whole function is continuous. Because the limit, as x approaches positive and negative infinity of f of x here, equals 1, and tangent of 1 equals whatever. I don't know what tangent of 1 is, but tangent of 1 equals whatever. So therefore, that's what they want you to use theorem 7 to show that the given function is continuous. So this is continuous because this is continuous, which gives me a value here, which showing that is continuous. There's no place where that's discontinuous.
So the value of tangent one is where the hole is.
No, there is no hole. I don't know what the tangent of 1 is, but it is a value.
But it doesn't, like, really matter though.
Correct, as long as it's not undefined. Because when I look at this limit is equal to 1. So I take my leading terms. Does that make sense? Take for instance, if you look at page 82. Show that y equals absolute value of x sine x over x squared plus 2 is continuous. So they divide it up. They say g of x is absolute value of x. F of x is x sine x over x squared plus 2. So if we know that the absolute value of g is continuous, absolute value of x, we know it's continuous, right? There's no breaks, there's no holes. Therefore, if that is continuous, then what we put in f of x is also continuous, because we have x sine x over x squared plus 2. There's no place where it makes it 0. So therefore, that makes the whole function continuous. And that's all they're showing. And we showed it this way. All right, I know that this is continuous because my limit as x approaches infinity equals 1. So there's no breaks in this. So therefore, when I put 1 into tangent, that equals a value, so that is continuous. So therefore, the whole function is continuous. So there's really no math. It's all concepts. And it's all, are you able to write down your thoughts that, okay, this is continuous throughout the whole domain. So therefore, my composite is continuous through the whole domain. Because remember, F circle, if I knew what x was, I would put x in for g first, get an answer, take that answer and put in the f. Okay, so the same thing here. I put a value in for here, so it doesn't matter what I put in here, the biggest number I can put, I'm basically 1, because that's my limit. So can I put 1 into this function and still get an answer? Yes. So therefore they both are continuous, so the whole function is continuous. Because that's what they're asking for. Okay? What's your other question, Noah?
Number 40.
Verify that the function is continuous and use this and state its domain. Indicate which theorem you are using and which function you are assuming to be continuous. Okay? So number 40, which function is continuous? Well, no, say verify the function is continuous and state its domain. So take for instance 40, the first part, x squared minus 1 over x plus, or x minus 1. Is that function continuous?
No.
No. Where is it not continuous?
1.
At 1. So therefore it is continuous where?
Everywhere but 1.
Everywhere but 1. Okay? So therefore, when they add down at 1, when they add 2, does the top equation equal 2 when I put 1 in, when it's simplified? Because basically we have this. we have x squared minus 1 over x minus 1, correct? So that's x minus 1 over x plus 1 over x minus 1. So when I cancel those out, I'm left with x plus 1. When x equals 1, what is it?
2.
2. So did that just fill in the hole?
Yes.
Yes. So now is my function continuous? Is y continuous?
No.
Yes. What is the domain?
Well, wouldn't it be not continuous because you're removable discontinuity?
Well, again, if I just take this function here, I have that. So the first function is not continuous. Because I have a hole. But when I add the second function to it,
You add,
it fills the hole in.
okay. And it's continuous?
So now is the function continuous?
Yes.
Yes. The function is continuous.
And the domain would just be,
Now the domain is all real numbers. Alright, now I'm not so worried about those problems as I'm worried more about the 47 to 50. Anybody have any questions on 47 to 50?
We didn't have to do, well, I guess we did have to do 48.
Here's 48.
Yeah, can we do 48? I think I have the right answer, but I'm not sure.
Alright? So here we got 2x plus 3 when x is less than or equal to 2. Alright? And as we talked about your piecewise functions, what was the best way to piece your piecewise functions together?
Does A equal 3?
Use the endpoints, correct?
Does A equal 3?
Does a equal 3?
So that's what you're trying, yeah. You're trying
Why
to
would
find-
a equal 3?
So you could, I don't know. Just
I got A equals 3 too.
But
See?
why would a equals 3?
because you're trying to get the thing together so it's not discontinuous. So it's all one
So it is
line.
continuous. So tell me, how do you figure out that a was 3?
Well, I figured out that the top equation, when you put in 2 for it, it started at 6. Right, that's where. No wait, it started at 7. I mean, and then so I knew you need to get the other one to get to 7. So I figured out.
Well, we didn't understand that.
What?
The first part we understood, but we didn't understand the second part. So how did you still get 3? You say, okay, I figured out that when x equals 2, that the top part is 7.
So what'd you
So how'd you go from there?
Then you plugged in 2 to the x in there in the second one and figured it out from there.
Figured out what?
That you needed 3 in A to get to 7.
Alright, so you set ax plus 1 equal to 7, and you put 2 in for x. So therefore, a equaled 3. Yes, that is the explanation that you could have finished. Okay, you just need to work on explaining and expressing your thoughts in words. But yes, that is the correct thought process, and that is correct.
Exactly why we can't.
A equals 3. Alright, any other questions on that?
I don't think so.
Okay. I will take those. We want to look at tangent lines today. Alright, tangent lines. We have this graph here, we got this is my linear equation, which is a secant line. A secant line is a line that intersects a graph at more than one point. So it intersects twice, so that's my secant line. Alright, the slope of this line represents what? What's the slope of that line represent? We have talked about this.
The slope.
Rate of change, alright, between my x and my y, correct? Rate of change, this rate of change represents what type of rate of change?
Upward.
It is a positive, but what kind of rate? What's that?
Exponential?
Nope. What do you say?
It's a linear rate,
What do you say after that?
rate of change.
No, I thought you said average.
That's what I said.
Is it?
Average. Average rate of change. This is f of b minus f of a over b minus a. That's my average rate of change. That's what we learned. Alright, then we had this equation that said the limit as h approaches 0 of f of x plus h minus f of x over h. So we said that if we make a second point and say that this second point is x plus h, and this is f of x plus h, and this is x and f of x. As h approaches 0, that means that this line is coming and coming and coming. And let's put this point right here because I want to put that point right there instead of down there. Until we get down to here, where x or h equals 0, I end up with a tangent line. Right? And this slope of my tangent line, this represented what?
The exact.
The exact or the instantaneous rate of change. The rate of change at that moment. And if I can find a slope of a tangent line, I can find the average or the instantaneous rate of change. And this is called the derivative. And that's what we're going to be dealing with the first half of calculus, is the derivative. Finding the derivative. The equation for the derivative is here. The derivative is instantaneous rate of change. The derivative is the slope of my tangent line. The slope of my tangent line. And if I take this line and move along the curve, you notice my slope is consistently changing. My rate of change of my slope is consistently changing. Is when I'm dealing with the tangent line. This represents the slope of my curve. The slope of my curve is limit as x approaches 0 of f of x plus h minus f of x over h, which is also determine the derivative. Alright, it's also determine the derivative. If this is my tangent line, then we learn in another course, this line here, the perpendicular line to my tangent line, is called my normal line. My normal line, what is the relationship between my normal line and my tangent line?
Opposite reciprocal.
Opposite reciprocal. So first of all, if I can find the slope of my tangent line, which I use this equation. I can find my normal line by using this equation to find my slope of my tangent line and taking the opposite reciprocal. Opposite reciprocal. So our goal here in this lesson is to practice using this equation. Now there is a shortcut to find derivative. But we're going to use this equation here for the next couple lessons before we use the shortcut. You may be able to figure out the shortcut after using this for a few times. All right? So let's look at some examples on page 92. Let's look at number 2, square root of 4x plus 1. They say find the average rate of change of the function over each interval. And number 2, they say the interval is 0 to 2. And they say the interval is 10 to 12. Are you with us? We're on page 92, and we're on number 2. All right, average f of b minus f of a over b minus a. So here we're going to have the square root of 4 times 2 plus 1 minus the square root of 4 times 0 plus 1 all over 2 minus 0. 4 times 2 is?
8.
Plus 1? Square root? Minus 4 times 0?
True.
0.
Plus 1?
1.
Square root?
1.
So we get 3 minus 1 over 2, which is?
1.
So my average rate of change between 0 and 2 is 1. Then I do 10 to 12, the same thing. Square root of 4 times 12 plus 1 minus the square root of 4 times 10 plus 1 all over 12 minus 10.
So we're finding average,
This is average rate of change.
and we're not finding the derivative now.
Not yet. Not in this section. 4 times 12
28.
plus 1
29.
square root
7.
4 times 10
40.
plus 1
41.
square root of 41 over 2. So 7 minus square root of 41 over 2 is my average. So find an average. Look down at number 8. It says the company figure shows the distance time graph for a wrench that fell from the top platform of a communications mast on the moon to the station roof 80 meters below. And there's the picture and there's the graph. All right? At the indicated points, find the slope of the curve. Wait a minute, 7, 8, no, 7, I'm on the wrong one. 7, estimate the slopes of the secants PQ1, PQ2, PQ3, PQ4. Arrange them in order in a table. What's the appropriate unit for these slopes? Find the speed at point P.
Where is it?
All right. So, we have this curve, P1, P2, P3, P4, I'm sorry, it's Q1. Q1, P2, P4. So they want the slope of PQ1 that means that slope. How do we find slope?
It's the derivative, it's the,
Just how do we find slope of a line?
oh, y over x.
Y over x, change of y, change of x, okay? So P's at 1080. Q1's at 520, correct? What's the slope?
We in a straight line.
The slope right here, from
12.
60 over 5. Alright, then we're gonna go Q2, PQ2, and Q2 is at what point? Come on, everybody, somebody,
Sorry.
7:39.
739? Alright, so my slope there is
41 over 3. I mean, 41 over 5. No, 41 over 3.
41 over 3, which is?
41 over 3.
What's 41 over 3? Put it in the decimal form.
Well, it'll be 12, no, it'll be, yeah, 12 point something, right? No, it'll be 13.
13.6 repeated.
Alright, then we want PQ3. Q3 is where? Kind of where is it?
On the X, right?
Look at the one graph.
It's at. So it's 7, 4, 39.
Q2, son.
Keep wrong, down the wrong one. Then Q3 is. Wait. So it's 8.5 and then 55.
Everybody agree?
Yes.
Alright, what's the slope there?
It will be, oh wait, I did that wrong. Well, 25 over.
It's like 23.3, right? No, 10.
25 over 1.5.
25 divided by 1.5?
16. Oh, no. 16.7. 16.7.
Does everybody agree? It seems a little high,
25 divided by 1.5.
correct?
16.6666.
Okay. And then PQ4? Real quick, before you leave, Q4 is
9.571.
9.5. And which one? What's the other point?
71.
71. So you get 9 divided by 0.5?
So
7.5 divided by 71.
no, 9 over 0.5.
9 divided by 0.5.
18.
18. Alright, so you notice as we get closer and closer to P, what's my slope getting closer and closer to?
20. I mean,
Bigger.
18.
18. So what do you think my slope at P would be?
8.
18.
Oh,
Okay, so that's what we're looking at, because this, as the secant line gets closer and closer and closer to the point, all right, you notice my secant, my tangent line slope gets bigger and bigger and bigger, correct? So we'll look at more of this tomorrow. What I want you to try to do tonight is to do numbers 1 through 13, every other odd. But I want you to do 13. If 13 is not part of it, do 13. 1 through 13, every other odd, but do 13.